Hi everyone, I hope you're all doing well. So in today's video, I'll be going through the 2018 physics exam multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Use the following information to answer question 1 and 2. A wire carrying a current of 10 amps is placed in a uniform magnetic field of this, as shown below. 10 centimeters of the wire is held in the field. As we can see, yes, only this part here is held in that field of that wire, and also 10 amps runs through it, and we also know that the magnetic field goes from north to south, so right to left, and of course current's going up. Whichever form best gives the magnitude of the force acting on the wire. Now, we know that there is a force produced because the current and the magnetic field are perpendicular, which is great. It means there is a force being produced. So the formula that we used to calculate that is the force is equal to N, the number of loops of the wire, times the length of the wire, the current, and the magnetic field. So in this case, N is just 1 because it's just a wire, so just one wire. Our length of that wire is 10 centimeters. Here's because you got to remember only this part is actually being affected by that magnetic field. So it'll be 10 times 10 to the negative 2 to change it to meters. Remember, not centimeters, but meters. The current, which is 10 amps, and the magnetic field, which is 4.0 times 10 to the negative 4. Easy. So using my calculator, let's get, what do we get? 10 times 10 to the negative 2, 10, 4.0 times 10 to the negative 4. That gives us, actually, 4.0 times 10 to the negative 1, 2, 3, 4. Negative 4, which looks like B is your answer for that one. Easy. Which of the following best gives the direction of the force acting on the wire? And this is easy because the way you do this is you look over here and you use the right hand slap rule. Your thumb, so you just do a like a slap, like you just, when you slap someone, so your thumb is the direction of the current, so your thumb should be acting upwards to this direction. So imagine your thumb in that direction, and your fingers are going to be in the direction of the magnetic field. As we can see, the magnetic field is going from north to south. So from my hand, I can see that palm of my hand is going towards me, so out of the page. Easy. Done. 2A. Nice and easy. A very kind of common question in exams, so 100% easy to do. Question 3. A straight wire carries a current of 10 amps. Which of the following best shows the magnetic field associated with the current, with this current? Of course, if you know that if there's a wire and you put some current, there will be a magnetic field generated. And the way you know the magnetic field is by using the right hand grip rule to show the direction. So imagine gripping your hand and your thumb upwards, and the thumb represents the direction of the current. In this case, it's upward. And where are your fingers going? Well, in terms of my fingers, they are actually going this way. So looks like A is your answer, as this is going this way. Done. So yeah, anti-clockwise pretty much. Yep, they're going anti-clockwise, so A. So that was nice and easy. Question 4. A small sphere has a charge of this on it. Take K as this. The strength of the electrical field due to this charge at 0.3 meters from the sphere is given by what? A nice, very typical question. So we know that the electrical field is given by K Q over R squared. And we know K is 8.99 times 10 to the power of 9. Q is the charge of the sphere, which in this case is 2.0 times 10 to the power of negative 6, all over the radius squared. So in this case, it's 3 squared. And let's check that. Now calculator, so 8.99 times 10 to the power 9, 2.0 times 10 to the power 6, 3 squared. And that gives me 1997, so 1997, which is the closest is D. That's, yep, the closest D, which is around 2000, the same as D. Easy. Question 5. 4 students are pulling on a rope in a 4-person tug of war. The relative sizes of the forces acting on the various ropes are this. So FW, which is actually this one, that's 200. FX, which is 240, means this one. FY, which is 180. And this is 210. The situation is shown in the diagram below. Which of the following gives the magnitude of the resultant force acting at the center of the tug of war ropes? Nice and easy. First, we're going to actually resolve the vertical forces. So, like 200 minus 180, we can see that there is an extra force going upwards, which is by 20. Yep. We're also going to resolve these forces. We're going to also add these forces also. So, adding these two, we will also get a force acting on the right, and it'll be going by 30. And it makes sense because 240 minus 210, which is 30, and it's on the right because this one's larger. And yeah, so we got these two. Now, if we put them together, this is actually not the resultant force. We have to put them together. So if I put this 30 over here and take that 20 and put it on the top, what we actually get is the resultant vector that comes up is this here over here. And this is our resultant force, finding this over here. And one of the easiest way is using Pythagoras' theorem to calculate that, because we have those two sides. And yeah, we just use Pythagoras' theorem. So Pythagoras' theorem, which is square root of 20 squared plus 30 squared. So square root 20 squared plus 30 squared, which gives me 36.05, which is C. The closest is C. Easy. Question 6. Lisa is driving a car of mass 1,000 kilograms at 20 meters per second. When she sees a dog in the middle of the road ahead of her, she takes 0.5 seconds to react and then brakes to a stop with a constant braking force. Her speed is shown in the graph below. Lisa stops before she hits the dog. That's good. Which of the following is closest to the magnitude of the braking force acting on Lisa's car during her braking time? Alright, so we want the force. You should know this formula should come to your head straight away. I is equal to F times T. Where this is your, what we call the force, the magnitude of the brake. We can get the magnitude of the braking force. This is the time that she took braking. And also that I is your impulse. Because luckily we have this graph over here that tells us the change in speed. And remember, impulse is just the change in momentum, which is just mv minus u. Force times time. The mass is 1,000 kilograms. The velocity, what's her final velocity? It's actually 0 because she came to a full stop. As you can see, she started at 20 and she was going, and she took half a second, so 0.5 seconds to realize, damn, there's a dog in front of me. She slows it down and her final speed is 0. 0 minus u. U is your initial velocity, and our initial velocity was before her. So when she was braking, it's actually 20 before she starts braking. So 20. Force times time. And what's the time? How long did she take to brake? Well, this is when she started to brake, and this is when she ended. So the time is actually 2.5. So that's actually, we can say negative 2, 0, 1, 2, 3 over 2.5, and that's your force. 2.5, and that gives me negative 8,000, which is pretty much 8, kilonewtons. Which is C. Negative means that it's going the opposite way, of course, because you are braking, the force is going to be the opposite. And yeah, easy. Question 7. At one point on the Earth's surface at a distance r from the center of the Earth, so imagine drawing an Earth, and so that is r. So yep, at one point on the Earth's surface at a distance r from the center of the Earth, the gravitational field strength is measured as 9.786, which is approximately 9.8, yep. Which of the following is closest to the Earth's gravitational field strength at a distance 2r above the, careful with the word here, above the surface of the Earth. So above the surface of the Earth, it means from here to somewhere here is 2r. 2r above the surface of the Earth. Easy! This question is actually one of the most repeated questions in exams. And I believe I do have a formula that helps me out doing these questions. It's one of my favorite formulas. It's this over here. I'll write it down. G1 over G2 is equal to R1 squared. So R1 and G1 are pretty much your beginning information. Like, for example, we know at a distance of R that G1 is going to be 9.76. R2 is, in this case will be 3R, because from the center to that point, 3R, what is the gravitational field strength? And then that's, we're pretty much trying to calculate G2. Easy. So what's G1? G1 is going to be pretty much 9.76. We're trying to calculate G2. R2 is what? It's going to be R3. Sorry, 3 R's. And R1 is R. So yep. And so square them, which these cancel out. And 3 squared is 9. So take that out. 9. Hence G2 is what? So G2 is just 9.76 divided by 9, which gives me 1.08, which looks like A is your answer. So yeah, I would absolutely put this in my formula sheet. It's one of the most helpful formulas for these kind of questions. You can not just use it for like gravitational field. You can actually use it for forces, but also you can use it for coulombs, like for example a charge. Because you remember, if you don't know, you can actually use charges have the same relationship, the inverse squared relationship. So yeah, absolutely would put this formula in my summary sheet. So question 8 and 9. A railway track X of mass 10 tons. 10 tons means 10,000 kilograms. Moving at 6 meters per second collides with a stationary railway truck of mass 5,000 tons. After the collision, the trucks are joined and move off as one. The situation is shown below. Beautiful. The final speed of the joined railway trucks after the collision is closest to what? You would have done these questions so much in year 12. These are the conservation of momentum. So, of course, the formula that should come to your mind is M1, U1, M2, U2 is equal to M3, V3, because these two are going to be colliding and they're going to be joined together. That's the key here. Of course, M1 is, in this case, this one. This is M2, and M3 are the addition of these two masses together. U1 means the velocity of this. U2 is the velocity of this over here, and V3 is the final velocity of the cut together joint. So we want to find V3, to be honest. So I'm going to write it as 10,000. So 10,000 means just 10,000. U1, which is going by 6, plus M2, which is 5,000. And it's actually times by 0 because it's actually stationary. So that's just useless. Is going to be equal to M3, which is the joined masses, which is just 15,000 V3. Hence, V3 is just 6,000 over 15,000. Let's check what that is. That gives me 4. Easy. Nice and easy. Question 9. The collision of the railway tracks is best described as what? Kinetic energy is conserved, but momentum is not conserved. We know, by the way, all this calculation that we've just done here is the conservation of momentum. Of course, 100%, we know that momentum is conserved. But the kinetic energy is actually, we have to question that. We can actually check if the kinetic energy is actually conserved. How? We check if it's an elastic collision. So what I would do in this case is to think about it like this. What's the kinetic energy before the collision? So, for example, I'll just say half. I'm not going to write 10,000. I'm just going to write 10. Just a quick 10. I'm going to write them in 10. So 10 times, I'm going to write it as 10 kilograms. This is 5 kilograms here. And velocity squared. So this will be still 0 because the velocity is 0. So it'll be, what's this? That is before. 0 0.5, 10, 6 squared. That's going to give me 180 joules. And now let's look at the energy. So these are going to be half 15 because they're joined. And the velocity that we calculated is 4 squared. So it's going to be 0 0.5, 15, 4 squared. Aha! There is some energy loss, some kinetic energy lost. It's not the same. So actually, kinetic energy is actually not conserved in this question. So the collision on the railway track is best described. Kinetic energy is conserved. Nope. Kinetic energy is not conserved, but momentum is conserved. Beautiful. That is the key there. Kinetic energy is not conserved, but momentum is conserved. Done. Let's go to the next question. Question 10. A loudspeaker is producing a sound wave of constant frequency. Consider a tiny dust particle 1 meter in front of this loudspeaker. Which of the following diagrams best describes the motion of the dust particle? We know loudspeakers create sound waves, and sound waves are longitudinal waves, so they move right and left. They just go right and left. There. So what's going to happen to that dust particle? It's going to be moving right and left. It's going to be oscillating between those positions. So D is your answer. This is a very nice, easy question. I think it was used in the past exams. Yeah, one of those past exams in VCAR. So these are one of the most common kind of questions. Question 11. Alex hears the sirens from a stationary fire engine. Compared with the sound Alex hears from a stationary fire engine, the sound Alex will hear as the fire engine approaches him will have increased what? All right. So if you don't know, say this is the fire engine. And it's actually approaching Alex. So let's call this guy Alex. As it's approaching him, what's happening is these waves are going to be, if it was further away, these waves will be having a very high, what we call wavelength. And remember, having a high wavelength means having a low frequency. So as it approaches him, he would hear it louder due to the case because it would have got smaller. The wavelength between the waves are actually getting smaller. If the wavelength's smaller, it means the frequency is very high. It's the frequency, and that's Doppler's effect. If you don't know, whenever you're dealing with Doppler effect questions, always think about the frequency. It's all about frequency in Doppler's effect. So the thing that really, anytime you're talking about Doppler's effect, it's all about frequency. So approaches him will have increased frequency. It's his frequency that increases. Easy. And as you can see, of course, the what we call the wavelength has decreased, hence the frequency would have increased. Easy, as I approached it. Question 12. A teacher sets up an apparatus to demonstrate young double slit experiment. A pattern of bright and dark bands is observed on the screen as shown below. Okay, beautiful. Which of the following actions will increase the distance change in X between the adjacent dark bands in this interference pattern? Easy. You do, guys, remember, you do have a formula for this. I'm just going to have a look at it. Where is it? Right over here. I've just took it from my summary sheet, and it's actually change in X, which is the, the distance between adjacent dark bands, lambda L D. This D here is the distance. It's the distance between the slits. So it's actually the slit separation. L is the distance from the double splits to the screen. This is your L. And of course, change in X is that. It's the distance between these two, the adjacent dark bands, and lambda is just a wavelength in this case. So let's have a look at the question. Which of the following action will increase that change in X? So we want to increase this. Let's have a look at which one will do that for us. Decrease the distance between the slit and the screen. So if you're decreasing the distance, you're actually decreasing L. So if you decrease L, it will decrease the change in X, and that's not what we want to do. We want to increase it. B, decrease the wavelength of light. If you decrease the wavelength, means decreasing this, you actually decrease the change in X again, so nope. C, decrease the slit separation. Yes, that's your slit separation, the D. So if you decrease that, it will increase this change in X, which is beautiful, C. D, decrease the slit width. Be careful. The slit width a lot of students actually might think the slit separation and slit widths are the same thing. No, the slit width will increase the intensity of the interference pattern, and it has no effect on the change in x, the distance between the adjacent bands. So yeah, C is your answer. 13. Which of the following diagram best represents the graph of the Lorentz factor versus speed for an electron that is accelerated from rest to near the speed of light? I remember kind of doing this question with some of my students, and those who did methods, it kind of helped them a lot. I'll show you how to look at in terms of equations if you do methods. So we know that the Lorentz factor is actually 1 over the square root of 1 minus v squared over c squared. And in this case, imagine that this is your y, and your speed is your x. So it means that this here, we can rub this, and we can call this actually just y, and this part x. Well, c squared is just a constant, so we can just imagine rubbing, not even worry about that, just actually put that still there. I've told my students many times that when they're dealing with this kind of graphing questions, we can see that there's the actual asymptote for all of them at C. And how can we prove that? Well, easily. We let the denominator equal 0. So imagine you let the denominator, of course that square root cancels out, so 1 minus x squared over c squared equals 0. 1 equals x squared over c squared. So c squared equals x, and hence c is equal to x. Here it is, at x equals c, so at v equals c, we will have an asymptote. And all of them actually have an asymptote. And what is an asymptote? An asymptote is you approach that value, but you never ever equal or never touch it. It just approaches close to it, but never approaches it. As you can see, B touches that value. Rubbish. Actually, A looks great. You know why? A, it's approaching it, but never touches it, so it looks good. And yeah, all the other ones look good. Now, how can we also look at another way? Have a look at the y-intercept. Well, this one's at 0. Let's actually just find the y-intercept if we're using this equation. Imagine finding the y-intercept, it's just letting x equals 0, so you'll just get 1 over square root of 1 minus, so 0, it'll be just 1 minus 0, which is just 1. So we're not at, when the speed is 0, lambda, or the Lorentz factor, actually is 1. It's actually never 0, so this is wrong. It's supposed to be a 1, positive 1. This is negative 1 approximately, so not that. And so it looks like D is your answer, where this is 1. And yeah, this is one of the most easiest graph to kind of look. But I just wanted to show some students how to do the maths. Like if you get a question and you don't know the maths, you just make an equation of it and start just using some, of course, by basic knowledge, you shouldn't really waste your time with this, but it's a very easy question. We know that the Lorentz factor must be greater or equal to 1. That's the first case. We always say lambda must be greater or equal to 1. So when we looked at lambda, we would have known that this one straight away A is wrong, because it would have to be greater than equal to 1, which this one is actually equal to 0. This one also C would have wrong, because it's less than, lambda is less than equal to 0. Yeah, so it would have been these two, but also we know that it will never actually approach that C value. This one does approach that C value, so absolutely not right. So yeah. Question 14. Which of the following statements about kinetic energy of a proton traveling at relativistic speed is the most accurate? The difference between the proton's relativistic kinetic energy and its classical cannot be determined. The proton's relativistic kinetic energy is greater than its classical. Okay. Well, let's just make some values, to be honest. This question is quite easy if you just make up values. Like, for example, let's say the velocity is for, let's say something that goes quick. It's like 2.99 times 10 to the power of 8. The mass is 1. And yeah, that's it. We just need this, because this is what we're going to do. We know for the like the normal kinetic energy that we do in classical is half mv squared. Yep. So we're going to write half. The mass is 1, so we can just write 1. And velocity 2.99 times 10 to the power of 8 squared. Let's see what that is. So 0.5. 2.99 times 10 to the power of 8 squared. That's actually just equal. So using your, so EK classical gives us 4.47 times 10 to the power of 16 joules. All right, now let's look at the relativistic one. Relativistic. Now, if you don't know, it's in your formula sheet. It's just your Lorentz factor minus 1 mc squared. So, what's your Lorentz factor? Well, it's easy because it's just 1 over the square root of 1 minus v squared over c squared, which is 1 over 1 minus, what's your velocity? We said our velocity is 2.99 times 10 to the power of 8 squared over c squared, which is 3.0 times 10 to the power of 8 squared. And let's just do that. Now, to be honest, I'm just having a look at it. I know for a fact that the relativistic will be greater. It's just because you got to remember c is actually being squared. So I would absolutely think that this must be greater. But yeah, just check. So 1 over square root 1 minus 2.99 times 10 to the power 8 squared, 3.0 times 10 to the power 8 squared. And that gives us 12 point, oh, did I? Yes, good. So yeah, 12.25. So so we can say that 12.25 minus 1, mass is just still 1, and c squared is 3.0 times 10 to the power 8 squared. Done. Let's do that. That gives us, wow, 1.0 times 10 to the power of 18 joules. So we know our relativistic must be greater than our classical. So the proton's relativistic is greater than its classical. So B. Beautiful. It was quite easily just guessing by looking at the formula, but I did want to show you guys how to do it by hand to show just a comparison of, yeah, the proton's relativistic is greater than its classical. Done. Easy. 15. Let's have a look at this. So when a beam of particles such as electrons passes through a narrow slit, diffraction effects can occur as shown in the diagram below. This phenomenon can be described as Heisenberg's uncertainty principle because when electrons pass through this slit, the uncertainty in there, beautiful. I've done so many of these kind of questions in past exams and they're one of my favorites. Here it is. Let me just explain what's happening. So imagine these electrons are moving to the right. And what's right? Isn't it the x direction? Yeah. So let's think about this. So the electrons are moving to the right. So what are we? We are certain, 100% certain that all of the electrons over here are moving to the right. 100%. Easy. But can we be 100% certain that all the electrons will pass through this narrow slit, which is actually in this y direction? You can see how that slit is in that y direction. Can we be 100% sure that all of these electrons will pass through that slit? That's where we have uncertainty. And so it's in that, we have uncertainty in that y direction in this case. So we have uncertainty in the position of y. And if you don't know, by Heisenberg's uncertainty principle, this is the key. The position y, or, the position y is always proportional to the, position, the momentum in the y direction. So for example, what do I mean? So if we have uncertainty in the position of y, we will also have uncertainty in the momentum in the direction of y. That's what Heisenberg's uncertainty states. It's just this kind of relationship. It's quite easy to understand. And yeah, whatever you have here must be, for example, if you have uncertainty in the y, you will have uncertainty in the momentum of y. If you have uncertainty in the x direction, you also have uncertainty in the momentum's x direction. Done. Let's have a look at the question. Y position does not affect the uncertainty in the y momentum. Rubbish, they do affect. B, y momentum affects the uncertainty in the x momentum. No, it will affect the momentum in the y momentum. This is supposed to be y here. C, x position affects the uncertainty in the x momentum. Now, that's true, 100%, but not in this case. In this question, that we have uncertainty in the y direction because we are 100% certain that in the x direction, we're not uncertain in the x direction. We know that they're going to go through we are certain that in the x position that the electrons will pass through, as we can see. But yes, D is your answer because it says y position affects the uncertainty in their y momentum, as we just stated here. A nice and easy marks to come out. 16. Polarization is a property of what? Remember, polarization, I've always said it to students, polarization only occurs for transverse waves. That's the key here. Always think of it like that. So, all types of waves? Nope. Be careful of that. B, only sound waves? No. Sound waves are longitudinal waves. C, only transverse waves? Beautiful. D, longitudinal waves are rubbish. Easy. 17. The results of a photoelectrical experiment are displayed in the graph below. The graph shows the maximum kinetic energy of the photoelectrons versus the frequency of light falling into the metal surface. Okay. The second experiment is conducted with the original metal surface being replaced with a larger work function. So we have a larger work function. So the original data is shown with a solid line, and the result of the second experiment are shown with a dashed line. Which of the following graph shows the result for the second experiment? You should know straight away that normally this over here, if it's actually drawn, this whole line, it's a straight line. When it crosses the y-axis, this here is actually your work function. Well, in this case, it will be negative, but yeah, it will be your work function. So if it's like, in this case, let's just say -2. But make it just positive. Work function, make sure it's positive. But because it's in the questions, the writer it's negative because it's below the y-axis, below the x-axis. So yeah, it will be -2. And so if you increase the work function, it will actually be like this. Now, can you see how now the work function, for example, now is -3? So you can see that the work function, to increase the work function, now the work function in this, so the original work function we said is not -2, but 2. Make sure it's always positive electrovolts. And the work function for the new one is actually 3 electrovolts. And remember, the gradients must be the same because Planck's constant, remember, Planck's constant is the same. So yeah, just from this actually, having a larger work function means that it would have been just translated to the right to give us a higher value. What a beautiful, easy question. So, A looks right. As you can see, the dash line is on the right. Yep, that looks good. 18. The experimental uncertainty in a measurement of any particular quantity is best described as what? So remember uncertainty. Let's have a look. A quantitative, so quantity good, say like a number, estimate of the doubt associated with measurement. Beautiful, that does describe it. Yeah, uncertainty. You have some doubt in your measurements. B, the degree of confidence a scientist has in the experimental. No, uncertainty is having a level of doubt. You're not confident. C, the difference between the measurement and the true value of the quantity. Nope. D, the result of one measurement repeated. So the result of one measurement, repeated measurements can eliminate uncertainty. No. Look, repeated measurements can decrease the random error, but they're not actually decreasing the systematic error, because systematic error is related to the equipment that you're using. And yeah, that's not going to eliminate all the uncertainty. So it is wrong. So choose A. A does describe what uncertainty is. A quantitative estimate of the doubt associated with measurement. Yeah, beautiful. 19. The diagram below shows a properly calibrated ammeter and its pointer registering a current of close to 3 amps. Which of the following is the most appropriate measure of the uncertainty of the pointer reading? What a beautiful question. This is one of the most kind of repeated questions in exams. The way you just determine the uncertainty for any measuring thing, for example, like this ammeter, is by looking at the small increments. So what is one small increment? It's actually just 1 amp, this one increment. So each increment here is going by 1. So, and you know what we do? We just divide it by 2. You take the smallest increment and you just divide it by 2, and that's your uncertainty. So you'll be 1 divided by 2, which is, in this case, it's just 0.5 amps. That's your uncertainty. For example, if I was like, we said it was 3 amps, you would write as 3 plus or negative 0.5 amps. That's how you'd write the uncertainty. So your uncertainty is just 0.5. Choose B. Nice and easy. 20. A group of physics students conduct a control experiment to investigate the phenomenon of electromagnetic induction. The students place a coil within a uniform magnetic field as shown in the diagram. Okay. The coil is spun at 50 revolutions per minute, 100 revolutions per minute, and 150 revolutions per minute. And the peak EMF is measured each time on an oscilloscope. Aha. What I can see is that they're actually changing the speed of the rotation, meaning that this must be your independent variable. Because remember, independent variable is the variable that you change. And the result of changing that independent variable is the dependent variable, which in this case is what we want to measure is the EMF. So your EMF must be your dependent variable. Whichever form best identifies the independent, dependent, and the possible controlled for this. Beautiful, easy question to end the exam. The independent variable, of course, is the speed of rotation. So the independent is the speed of rotation, so C and D are wrong. And the dependent variable, as we said, is the peak EMF, because that's what we're measuring. So looks like B is right. As you can see, peak EMF, done. And yes, control variable is the strength of the magnetic field. That's, that value is constant throughout the experiment. And yes, as it is saying here, a uniform magnetic field, done. Thank you guys for watching, and please make sure like and subscribe for more videos. Please share it with your friends, and I hope you have a great day. Take care of yourselves.